So let's continue. With this very simple proof, which in fact we have already seen the way we have produced this result, but just to check that we are not missing any detail. So to prove monotonicity, let P and Q be price vectors. X belong to X of P, and Y belong to X of Q. Then it's clear that the pairs Px and Qy belong to the set we call C, because Px belonging here simply means that X is preferred to any commodity bundle compatible with P. And this is the case, because X is optimal under P. On top of that, Px is less than or equal to 1, but we don't care at this moment. The same with the pair Qy. Then, because we are assuming convexity, then we have 1/2 P plus Q, comma 1/2 X plus Y belongs to C. I don't know anymore if 1/2 X plus Y satisfies the budget constraint under these prices or not. I don't care. But the pair belongs to this set. And this simply means that 1/2 X plus Y is preferred to any set that satisfies the budget constraint corresponding to 1/2 P plus Q. Okay? And now we proceed as in the original proof, the first proof I gave you this morning. This means that 1/2 P plus Q times 1/2 X plus Y must be greater than or equal to 1. Why? In the proof we made at the beginning of the session this morning, the assumption that came into play was the non-existence of a maximum. So here it should be the local non-satiation property. Yeah, so assume for a moment that you have strictly less. Then this commodity bundle is affordable under these prices, but cannot be optimal. Because if it were optimal, at this point we would have satiation. Okay? So, I mean, around this point there is something better. If it is close enough to this point, that it still satisfies the budget constraint. So the previous one cannot be optimal because there is something better. Okay? And this is only possible if this is greater than or equal to 1, and now the proof ends as in the first result we saw. Write 1 in a clever way. This is a clever way of writing 1 in this situation, because again for the local non-satiation property this is equal to 1 and this is equal to 1. This is less than or equal to 1 because this is feasible under P, the same here, and cannot be smaller than 1 because the local non-satiation property, so it must be equal to 1. And now you see that a very simple algebraic manipulation yields the monotonicity condition. Is the only result I know, because I think economists have not addressed this problem of examining monotonicity without differentiability of the utility function, let alone without utility functions. So they never consider, as far as I know, the demand for just preferences. Okay? So this is the only result I know, which I produced, still unpublished. And so I like it, but I'm not extremely proud of it. Why not? Because it's very far from what I would like to obtain. I would like to obtain if and only if. This is very far from being if and only if. And second, I have no reasonable economic interpretation of the convexity of this set. So what does convexity of this set mean from an economics point of view? I don't know, I have no clear interpretation of that. Okay? And but now the question is, again, this set is not a primitive. The primitive is the order relation. So which properties on the preorder guarantee that this set is convex? So I don't know. Well, I know very little. I can give you a property which guarantees this convexity, but it's not a very exciting result. So now I'm going to address now convexity of this set. So when you add, I'm going to give you a sufficient condition. So when you add that sufficient condition to the local non-satiation property, you get a sufficient condition for monotonicity. Okay? So suppose X satisfies the following property. Whenever you have three commodity bundles, X1, X2, Y, in R plus N, and two positive numbers, lambda and mu. And they are such that x1 is preferred to lambda y, x2 is preferred to mu y. So the property is that in this situation, 1/2 plus x2 is preferred to twice lambda mu over lambda plus mu y. Well, an important comment. I mentioned that in the utility representation case, relaxing concavity to midpoint concavity and convexity to midpoint convexity was pointless, but not here. Okay? I mean, because this set need not necessarily be closed. So, in fact, we only need, in the previous statement, instead of writing that this set is convex, you can write midpoint convex. When you add closeness, then this means simply convexity. Okay, but let's consider the general case of midpoint convexity. Then, let's call this property P. If proposition if this satisfies P, then this is midpoint convex. The set is midpoint convex. Let's prove it. So we take 2 points, P1x1 and P2x2 in the set, and we want to deal with the midpoint. And to compare the midpoint between x1 and x2 with any commodity bundle that is affordable under the price vector midpoint of P1 and P2. So I consider any commodity bundle which is compatible with this price vector. Then I will consider 3 cases which are dealt with very similarly. So first case, there is no P and Q. There are P1 and P2. So I consider first case both P1y and P2y are strictly positive. Second case will be when one is strictly positive and the other is 0. The third case will be when both of them are 0. They are non-negative, okay? The cost is always non-negative. In this first case, then I claim that x1 is preferred to 1 over P1y times y. Do you agree? This is a consequence of the fact that the pair P1x1 is in this set, and the fact that this particular commodity bundle satisfies this budget constraint with P1, because P1 times this is equal to 1. Okay, then this immediately follows from this definition. And in the same way, x2 is preferred to 1 over P2y times y. And then I can apply the property, the very strange property, but I will make comments about this property later. Okay? The very strange property I am assuming. Then, because of that property, 1/2 x1 plus x2 is preferred to twice lambda mu. Lambda is 1 over P1. Mu is now 1 over P2y. Something important is missing in this statement, which we will see the need for it, okay? Rather than correcting the statement now, I postpone it to the moment when I see that we need it. Then, this is simply one over P1y plus P2y times y. We know this condition, which means that this coefficient is greater than or equal to 1. What is your conclusion? No conclusion, unless we assume, on top of the given assumption, that our preferences are so-called non-decreasing. I forgot to introduce this definition, and for this reason I forgot to introduce this assumption. Is non-decreasing what What does it mean? It means that for you, better is more is better. This means that, so one says that is non-decreasing. Means that whenever you have xy with x greater than or equal to y component-wise, so x is more than y, this commodity bundle has more of every, or at least the same of every component, then you prefer x to y. Quite reasonable assumption. If a preference ordering or total pre-ordering is non-decreasing, every utility representation, if it has, is non-decreasing, and vice versa. If you have a total pre-order represented by a non-decreasing utility function, it is clearly non-decreasing. Then if one utility representation has this property, every other utility representation has that property too. Okay, so here was the condition that was missing. Because this is greater than or equal to 1, this times y is greater or equal to y. But now, if more is better, being greater than y means that this is preferred to y. Okay? So, by transitivity, we have that this condition is satisfied, and so the pair one half P1 plus P2, one half X1 plus X2 belongs to this set, as had to be proved. Okay? But we have needed the assumption of non-decreasingness. Let's try to prove the other cases. They are very similar. No, still. Okay. So now I consider the case when one of the two, let's say P1 of X1, is strictly positive, and P2 of X2 is 0. This is possible because prices may be 0, have some 0 component. Okay? By symmetry, we don't need to consider later the case when P1 X1 is 0 and P2 of X2 is strictly positive. Then, in that case, what we have to use is that X1 is preferred to 1 over P1Y. Y, and that X2 is preferred to 1 over 2 minus P1Y times Y. Well, the first, this is true, we already discussed about it, no? But for the second, The second would be true given that P2x2 is in this set. So the second would be true if this multiplied with P2 is less than or equal to 1. Let us see if this is the case. P2 times this vector is, and by the way, this number is positive because we are comparing with y in R plus n such that 1/2 P1 plus P2 y is less than or equal to 1. This is the comparison that we are making now. Okay, then since this means that P1 plus P2 y is less than or equal to 1. But wait a second. So the distinction is not with x1. So we started saying what happens with this is positive and that is positive. The second case is with the same numbers, y, not x1, x2. Okay? Then, if P to y is 0, sorry, and this is 2, if P to y is 0, this simply means that P1y is less than or equal to 2. It can be seen to be strictly less than 2. But I don't see why. Do you see any reason why this should be strictly less than 2? No, because this would imply that this is less than, strictly less than 2. So maybe, yeah, I was thinking about that, but if instead of 2 we take 1, this may be even negative. We only know that this is less than or equal to 2. No. Okay. There is 1/2. Okay, if you want. So this is not correct, but maybe the strategy is different. Otherwise, this should work only for strictly positive prices. This is what I wrote yesterday, but now I noticed that there is this flaw. Should we try to repair it now? Let me try. Okay, but I have to change everything completely. In this case. So instead of writing this, I claim, but I'm not sure, that this is greater than or equal to mu y for which mu's? I think for every mu, no? Because if you compute P2 mu y, then this is 0 because P2y is equal to 0. No? Then, so this is true for every mu. Let us try if this works instead of what I did first. Then, there will be no.
There is nothing to compare because mu is 0. When we apply the formula.
No, mu is any mu. So when we apply property P, we have 1/2 x1 plus x2 referred to twice 1 over P1y times mu divided by 1 over P1y plus mu times y. And probably, I guess, there is some mu for which this quotient is, hopefully, is greater than or equal to 1. Is there such mu? Is there mu such that positive, such that this is greater than or equal to 1 or equal to 1? We can try to solve the equation, this equal to 1, and see if the corresponding mu is positive or not. Here is P1. Okay? So if we move this to the right-hand side, what we get is mu multiplied with 1 minus 2 over P1y less than or equal to, no, this multiplied with mu, less than or equal to 1 over P1 over y. Is this correct? No, with minus. Less than or equal to. And what can we say about this coefficient? This is less than or equal to 2, but it could be 2. But we only need this inequality, but we need this we need this inequality with mu positive. If this coefficient is 0, which could be the case, then every positive mu, no positive mu because the right hand side is negative. So if this is 0, as before we have a problem. So we have to distinguish subcases. If this is equal to 2, so it was not so simple as I was considering. Should we try to complete the proof now or together, or do you prefer me to prepare at home and then to show you? What is better? We do it now? We try? Okay. Let us see. So it seems that the difficulty is in the fact though of P1 y being equal to 2 in the case when P2y is equal to 0. I think if you want to save a lot of time, there is a nice possibility to assume that our preorder is continuous. Continuous means that its graph is closed. Then if that property holds with lambda positive and mu positive, we can make lambda and mu tend to 0, and that's it. But okay, this should be a little bit tricky. So the condition is, so what happens when, we saw that this doesn't work when P1y is equal to 2. So let's assume now that P1y is strictly less than 2. And P2y is equal to 0. Okay? Later we will consider the case when this is equal to 2. Then when we come here, then this is strictly negative, so we can solve for mu and we get a mu positive that does the job. And that's it. So now the problem, we are going to have troubles when we have P1y equal 2 and P2y equal 0. For x, of course, I use that this is greater than or equal to 1 over P1y times y. And for x2, what should I use? So at this point, I wanted to use that the preorder is non-decreasing. Okay, here. But it didn't work in this case as we saw if the coefficient is non-positive, is 0, sorry. So we get this coefficient, but then in this case, P1y is equal to, so we get mu divided by 1/2 times mu. Let's see if it works. So I am assuming this greater than or equal to mu y. So the conclusion is, let us see if it is useful or not, that 1/2 x1 plus x2 is preferred to mu over 1 plus mu, 1/2 plus mu, times y. Well, we indeed need to assume. We need to assume continuity of the preorder. I see no other solution. Because this was true for every mu. So if we let mu go to plus infinity, this tends to 1. And then going to the limit, we obtain this is preferred to y. But I have used continuity of the preorder. So this is missing in the statement. I only noticed now. I had the proof first for r plus plus n. And now I see that to extend it to r plus n, we need this continuity property. Is the proof now clear, or should I repeat? Still one case is missing. I hope it will not create the same trouble. So the correct statement is, if it is continuous. I told you these results are not published. And non-decreasing, and satisfies property P, then this set is midpoint convex. Okay? So initially I simply said satisfies P, then I realized that we have to add non-decreasingness, and now I realize that we have to add continuity of the preorder. Okay, good. Let us see if the third case gives us some troubles or not. The third case is both P1 y and P2y are equal than or equal to 0. Then x1, let me see if it is, I want to check if what it's easier than what I wanted to do. Yeah, it's much easier. I was going to play with lambda and mu arbitrary, but there is no need. So then x1 is preferred to y, because P1 x1 is here, which means that I prefer x1 to anything which is affordable under P1. And of course, x1 is affordable, it's free. The cost is 0. Okay? So x1 is preferred to y. x2, for the same reason, is preferred to y, because also P2y is 0. So property P holds with lambda and mu equal to 1. Then 1/2 x1 plus x2 is preferred to, for lambda and mu equal to 1, we get 1. That coefficient 2i is lambda mu divided by lambda plus mu is 1. So I directly get, without playing with any lambda and any mu, just lambda and mu equal 1 do the job, I obtain the conclusion. Okay, so 1/2, in this third case, I also get that the pair 1/2 P1 plus P2, 1/2 x1 plus x2 belongs to C. So the proof is complete, but after adding these necessary assumptions. But this property P is very strange. Let us write it again and let's make some comments. Well, it's strange, but it's often satisfied. Suppose that the graph of our relation, our preorder is non-decreasing, and has a convex graph. I will comment about this assumption. Then property P holds. And therefore, if our preorder is non-decreasing, continuous, and has a convex graph, then demand is monotone. But I will comment about the assumptions. Why? Because, again, let's consider the situation when we have P1x1 and P2x2 in the set C, and then assume that x and lambda and mu are positive, and assume that we have also for some y x1 prefer to lambda y and x2 prefer to mu y, uy. Then, of course, x1 lambda I, lambda y, and x2 mu y are in the graph. Okay? And then by convexity, midpoint convexity would be enough. If you want to relax, right here, midpoint convex. Okay. But I'm not very excited about such kind of relaxations, moving from convexity to midpoint convexity. Then this means that 1/2 x1 plus x2, 1/2 lambda plus mu y is in the graph. So this means that these conditions imply that 1/2 x1 plus x2 is preferred to 1/2 lambda plus mu y, but 1/2 lambda plus mu is greater than or equal to twice lambda mu divided by lambda plus mu. Okay? As is easy to check. In fact, this at first sight strange coefficient appearing in condition P is not so strange. It's the harmonic mean. This is 2 divided by 1 over lambda plus 1 over mu. So the harmonic mean, you take the reciprocals, their mean, and then take the reciprocal again. Okay? And it's well known that the arithmetic mean is greater than or equal to the harmonic mean. But it can be proved directly here. So here you have that lambda, this condition is equivalent to lambda plus mu to the square greater than or equal to 4 lambda mu, which simply means that lambda minus mu to the square is not negative, okay, which is true. Okay, then in this case, we have this, and because the arithmetic mean is larger than the harmonic mean, you have this greater than or equal to twice lambda mu divided by lambda plus mu y. But our preorder is non-decreasing, so more is better. So this is preferred to y. And this shows this shows, can you still hear me? Yes. So this shows that the pair 1/2 P1 plus P2 1/2 x1 plus x2 is in our set C. So our set C is convex, but actually we just needed to know that the property P holds, and this was already proved here. Okay? But now, what about the assumptions we are using? So property P is very strange. I have no economic interpretation. But what about convexity of the graph of the relation? Is it an acceptable property from an economics viewpoint? What do you think? Convexity or mean point convexity of the graph of the relation means that if you have x1, y1 in the graph and x2, y2 in the graph, then 1/2 x1 plus x2, comma 1/2 y1 plus y2 should also be in the graph. So in particular, suppose we are in R2 and x1 is 1, 0 and x2 is 0, 1. This means that okay, and y1 is 0, 1. Okay, and if you want, y2 is 1, 0. Then remember the example with you are in the desert and I offer you 1 liter water and 1 kilo bread. You have to choose, or 1/2, 1/2. Then the situation here would be that if one is water, you prefer u of x1, you prefer x1 to y1. The point is that, let me express you in a much simpler way. This implies two things. This implies that when you have x1y and xyy in the set, then by convexity, 1/2 x1 plus x2 y is in the set. Which is reasonable. You prefer, we are saying that if x1 is preferred to y and x2 is preferred to y, then 1/2 x1 plus x2 is preferred to y. And this is quite reasonable. But in the same way, you are assuming that if you have xy1 and xy2 in the graph, then x 1/2 y1 plus y2 is in the graph. Which means that u of x or x should be preferred to 1/2 y1 plus y2. And this is not reasonable. Again, the example is water and bread. 1, 0 and 0, 1, where 1 is water, the first component is water, the second component is bread. Okay? Even though you prefer water to bread, you don't prefer 1 kilo water and no bread to 1/2 kilo water and 1/2 kilo bread. So convexity of the graph is too strong. It implies a property which is nice because it expresses your preference for mixing, but it also expresses the opposite. It's too strong. So it's unreasonable. So I'm not very proud of having obtained all these conditions, but it's all I can offer. Okay? So the conclusion now, roughly speaking, is that if the graph is convex and something else, non-decreasingness, the demand is monotone, but this convexity of the graph is an acceptable assumption from an economics point of view. Mathematically, it's very nice, but economically, no. And second, because it's not acceptable, the converse is very far to be true. I mean, having a monotone demand does not imply any convexity property of the graph. But this opens an avenue for further research. Probably too difficult, and this is the reason why I stopped many years ago. But I don't know, some of you, maybe you are young and full of energy, and maybe you can try to work on this problem. Oh, it's the time? No? No. No, we still have time or no? No. Then, okay. So we'll continue with the same or related topic.